Ever get that feeling your computer has, like, hidden turbo boosters that aren't quite firing right?
Yeah, like there's performance just sitting there untapped.
Exactly. Well, today we're pulling back the curtain on two of these under the hood settings. They have a surprisingly big impact on how fast your data actually moves.
Ah, you're talking about maximum payload size, MPS, and maximum read request size, MRRS.
That's them. Think of it as understanding how the data trucks operate on your computer's internal highway system, the PCIe bus.
Right. And what's really fascinating, I think, is that tweaking these seemingly small, pretty technical parameters can genuinely translate into performance differences you might actually notice.
Yeah.
So we're going to try and break down what MPS and MRS are all about and, why they're so critical for keeping things running smoothly quickly.
Right. So our mission in this deep dive is simple. Make MPS and MRRS clear. Make them understandable. We want you to finish this feeling like you've unlocked a secret level of knowledge about your computer, without needing a PhD in electrical engineering.
Definitely. Consider it a shortcut to understanding a really key part of your system's potential.
So the bigger picture, PCIe, Peripheral Component Interconnect Express.
That's the superhighway, right? For all the high-speed data zipping around inside your machine.
Absolutely. And efficient traffic flow there is just essential for everything from, say, smooth gaming frame rates to how fast your files transfer.
Okay.
And MPS and MRS, they're kind of like the traffic laws on that highway. They dictate how data gets bundled up and how it's requested, all to keep things moving efficiently.
And here's a cool bit. They aren't set in stone.
No, that's key.
MPS and MRS are configurable settings. It was kind of like adjusting the gears on a bike.
Right.
Gives us the potential to fine-tune for better performance, but also means we could, accidentally shift into the wrong gear if we don't understand what we're doing.
Which brings up a really important question.
Right.
How do these settings, which sound pretty obscure, actually affect the speed and responsiveness you feel every day?
We'll be exploring how MPS and MRRS can influence everything from, how quickly your graphics card grabs textures in a game to how long you wait for that massive video file to copy.
Okay, let's dive in. Starting with maximum payload size, MPS.
Right.
So MPS, in simple terms, what is it exactly?
Okay, think of MPS as the maximum cargo capacity for a single data packet traveling on that PCIe bus.
Okay.
Officially, it's the largest amount of actual data measured in bytes that can fit in the main data section of a PCIe packet. We call that packet a transaction layer packet.
Right.
Or TLP.
Right, TLP.
So
Yes.
it's just like the size limit for one single shipping container on our PCIe data highway analogy.
A shipping container. So why not just make these containers, huge all the time? Wouldn't that always be faster to send more data at once?
That's a really good question. The reason for having an MPS limit is actually to allow all the different devices on the bus, graphics cards, network cards, SSDs, to agree on a packet size they can all handle comfortably.
Yeah.
It's a trade-off, really. Larger packets can be more efficient, because they cut down on the overhead, the addressing and error checking stuff for sending lots of smaller packets.
Right.
But they also need more buffer space in the receiving device to actually hold that bigger chunk of data while it's being processed.
So if a device isn't ready for a huge packet.
Exactly. If it's not equipped to handle it, you could get errors, maybe even lost data. So it's about finding a common ground.
So it's a negotiation then, like agreeing on the size of those shipping containers. Both the sender and the receiver have to be okay with the size.
Precisely. When a device sends data, it will only make packets with a data load up to whatever its configured MPS is. And on the flip side, the receiving device has to be ready to accept and process packets that are potentially as large as that agreed upon MPS.
What sort of sizes are we typically talking about here? Are there standard options?
Yeah, the PCIe standard defines a set of common sizes. They're powers of 2, usually ranging from 128 bytes up to 4096 bytes.
Okay.
So you'll see options like 128, 256, 512, 1024, 2048, 4096 bytes, doubling each time.
All right, so how does a device actually know which MPS value to use? Is there some kind of digital handshake going on?
Absolutely. This negotiation happens when your computer boots up. Every PCIe device has these configuration settings stored inside it.
Right.
There's something called the Device Capabilities Register. That's where a device basically announces, hey, look, these are the biggest packet sizes I can comfortably handle.
Okay, it's potential.
Exactly. Then the system software, maybe the BIOS, maybe your operating system later on looks at all these announcements, and it sets the actual MPS the device will use day to day. That's done in a different register, the device control register.
Ah, so there's what it could do and then what it's actually told to do.
Precisely. And the
Yeah.
way these values are stored, it's quite specific, using just a few bits in those registers. The technical detail isn't super important for users, but the key takeaway is that this setting, however it's encoded, directly impacts how efficiently you can transfer large amounts of data. Smaller sizes mean broader compatibility, maybe, but larger ones potentially give you better performance if the devices can handle it.
That's a neat bit of behind-the-scenes communication. Now, you mentioned this negotiation. What happens if different parts of my computer, say my graphics card and my motherboard's chipset, support different maximum MPS values?
Right, this is where it gets really interesting and kind of crucial for performance. The operational MPS for any data transfer on the PCIe system is limited by the device with the smallest MPS capability along that entire communication path.
The weakest link, right?
Exactly, the weakest link principle.
Ah, okay. So it's like a water pipe.
Huh.
The narrowest section restricts the flow for everything. So even if my super fast new SSD supports, say, 4096 byte MPS,
Yeah.
if it's connected through, I don't know, an older switch chip on the motherboard that only supports 256 bytes.
Then the communication between your CPU and that SSD going through that switch will be limited to 256 byte packets.
Wow. Okay.
And that has real performance consequences. A single component with a low MPS can effectively bottleneck the efficiency of an otherwise high-performance system because all devices talking through it have to use those smaller packets, which means more overhead for the same amount of data.
That makes total sense. So is it always just about finding that single lowest MPS in the entire system then? Does everything run at that speed?
Not necessarily, especially in modern computers. Operating systems like Linux have gotten smarter. There's a setting, Cybusperf, that allows for a more hierarchical approach.
Hierarchical, how does that work?
It means different sections or segments of the PCIe highway can potentially operate at different MPS values.
Ah,
So maybe the connection between your CPU and your graphics card can use a large MPS if they both support it, even if some other part of the system is limited to a smaller MPS.
okay.
The crucial rule, though, is that any single data packet still has to respect the MPS limit of every single device it travels through on its specific path.
Right. So you don't get dragged down everywhere, but any specific conversation is still limited by the slowest talker in that chain.
You got it. It's a much more efficient way to manage things overall.
Okay, so MPS is all about the size of the data packets themselves. Now let's switch gears. What about this other setting, maximum read request size, or MRRS? What's its role?
Okay, MRRS. This one specifically deals with read operations. So when a device wants to pull data from somewhere else, like from your main system memory,
Right.
MRS defines the largest size, again in bytes, of a single request for data that a device, acting as the requester, is allowed to make.
Okay, wait. So MPS is the size of the data payload being moved,
Yeah.
and MRRS is the size of the ask for data.
That's a perfect way to think about it. Exactly. And MRRS has a couple of main benefits.
Okay.
First, it makes the whole process of requesting reads more efficient. Think about needing a large file, right? You could ask for it one tiny piece at a time.
Like asking for a book word by word. Sort of. Or you could ask for larger chunks, like chapters or pages. Each request itself has some overhead. Please send data starting from this address part. It's not just data. By allowing larger read requests up to the MRS limit, you drastically reduce the number of these overhead-heavy request packets you need to send to get the same total amount of data.
Okay, can you give me a feel for how much overhead we're saving? Like a practical example.
Sure. Let's imagine your graphics card needs, say, 64 kilobytes of texture data from RAM.
Okay.
If its MRS is set really low, maybe 128 bytes, it would have to send out 512 separate read this little chunk request packets.
512 requests. Wow.
Yeah. But if its MRS is set to a larger value, like 496 bytes or 4K, it would only need to send 16 requests to ask for that exact same 64 KB of data.
16. That's a huge difference.
It really is. It's a massive reduction in just the request traffic itself.
So fewer requests mean more of the system's time and PCIe bandwidth are actually available for moving the data itself, not just asking for it. Exactly. And the second main purpose of MRRS is it gives the system software like the OS a way to manage bandwidth allocation.
Oh, so...
By putting a limit on how much data any single device can ask for in one go, the OS can sort of prevent one greedy device from hogging all the memory bandwidth, or maybe overwhelming the device that's supposed to be providing the data. It's a control knob.
Okay, that makes sense.
Mm.
So what are the typical MRRS values? Are they the same power of 2 range as MPS?
Not quite the same steps. MRRS is also configurable, and it generally ranges from 128 bytes up to that same 4096 byte maximum. But it's usually set in increments of 128 bytes. So 128, 256, 384, 512, and so on, up to 4096.
And where do we find these settings? Is it in that same control register as MPS?
Yes, typically MRS is configured in that same device control register we talked about for MPS. Usually it's a specific set of bits, like bits 14 down to 12 in the standard configuration space.
Yep.
And just like MPS, you can often view and sometimes carefully change the MRS using tools like elsebyte to view and setkai to potentially modify, especially in Linux systems. There's a similar encoding scheme for the value based on those bits.
So the really key thing to keep straight here is MRS is the size of the request, the ask.
Right.
And MPS is the size of the payload in the packets when the data actually comes back or when you're writing data.
That's the crucial distinction, yes. A large MRRS lets you ask for a big chunk efficiently, but it doesn't automatically mean the data will come back in equally large packets.
Ah.
The size of those return data packets is still governed by the MPS of the device that's sending the data back, the completer, and also by these things called read completion boundaries, which we should probably talk about.
Okay, yeah, you mentioned those. But first, this idea that MRS can be larger than MPS, that feels a bit counterintuitive. How does that actually work? If I ask for, say, a 4KB chunk with my MRRS, but the system's MPS is only 512 bytes, what happens when the data comes back?
All right, this is another layer of how PCIe manages things. When a device makes a read request that's bigger than the current operational MPS, but still within its allowed MRRS, limit the device providing the data, the completer.
The one sending it back.
Exactly. It has to break that large chunk of requested data down into multiple smaller packets for the return trip.
Okay.
These return packets are called completion with data TLPs, or CPLD TLPs. And each of these individual return packets will have a data payload that's no larger than the completer's MPS setting.
Oh, okay.
And they also have to follow these rules related to the read completion boundary, or RCB.
Okay.
The device that made the original big request then has the job of collecting all these smaller CPLD packets as they arrive and reassembling them back into the complete 4KB chunk it asked for.
So I send one big give me 4KB request thanks to my large MRRS.
Yep.
But the data comes back potentially as, say, 8 separate 512 byte packets because that's the MPS limit.
Exactly. Or maybe even more packets if the RCB rules force smaller chunks, which we'll get to.
This explains why you often hear that guideline, right? That for optimal performance, especially in systems with mixed hardware, maybe MRRS shouldn't be set way larger than the operational MPS.
Yes, that's a common recommendation, and it's sort of the philosophy behind that Linux CIVIS setting we mentioned.
Why is that the thinking? If a larger MRS is more efficient for the request, why limit it based on the return packet size, the MPS?
Well, the rationale is about preventing potential inefficiencies down the line. If you have a device with a, let's say, low MPS, maybe only 128 bytes, but you allow it to make really huge read requests because its MRS is set very high, say 4096 bytes,
Right.
then the system is going to have to chop that requested 4KB of data into 32 separate 128-byte return packets anyway.
I see.
That fragmentation and reassembly process could potentially add complexity or latency, especially if the system is busy. It might not actually give you the best overall throughput or responsiveness in that specific scenario.
So keeping MRS more in line with the local MPS, especially in those smarter hierarchical setups, is about aligning the request size with how the data can actually be delivered efficiently.
Pretty much. It aims for a more balanced performance, making sure requests aren't wildly out of sync with the system's capability to fulfill them in reasonably sized chunks.
But it's a guideline, not a hard rule.
Definitely a guideline. The truly optimal choice always depends on the specific system architecture, the devices involved, and exactly what kind of performance you're trying to maximize, raw throughput, low latency, etc.
Okay, so we have MPS for packet payload size, MRRS for request size, and now you've brought up this read completion boundary, RCB, a couple of times. Let's tackle that. What is it, and how does it fit in?
Right. The read completion boundary, RCB, think of it as like an invisible grid line drawn across memory addresses.
Okay.
Typically, this grid line happens every 64 bytes, or sometimes every 128 bytes. It's a naturally aligned boundary.
So address 064, 128, 192.
Exactly. And the RCB dictates how the data coming back from a read request, those CPLD packets we just talked about, gets segmented or split up.
Mm.
It's like a rule saying the returning data packages need to sort of respect these grid lines. You might see RCB mentioned in technical docs for certain hardware, like some FPGAs where it might even be configurable.
Okay, so it's another rule for chopping up the return data. Why is that necessary? MPS wasn't enough.
It provides a standardized, predictable way for the completer of the device sending the data back to segment it. This makes it easier for the requester to manage its incoming data buffers. It knows data chunks won't just end randomly midstream. They'll align to these boundaries.
Okay, so what are the rules then? How does RCB interact with MPS?
Okay, here are the main rules for how read data gets packetized using MRRS, MPS, and RCB.
Right.
First, the very first completion packet starts exactly at the memory address you requested. Makes sense.
Yeah.
Second, any intermediate completion packets, the ones in the middle of a large transfer, must start and end neatly on those RCB boundaries. The payload size of these packets can be up to the MPS limit, but they cannot cross an RCB line.
Ah, so even if MPS is 128, if the next RCB is only 64 bytes away, the packet might only contain 64 bytes.
Precisely. The RCB boundary takes precedence there.
Okay.
Third, the very last completion packet just finishes at the final address of your original request. Even if that doesn't line up perfectly with an RCB, it just contains whatever data is left.
Got it. And the key is no single packet crosses an RCB line.
That's the fundamental rule.
Yeah.
A single CPLD payload cannot span across an RCB boundary. It has to fit entirely within one RCB box, starting either at the requested address or an RCB line, and ending either at an RCB line or the final requested address.
Can we walk through a quick example how MRS, MPS, and RCB work together?
Sure. Let's say you use your MRS to request 200 bytes of data, starting at memory address 0 by 1000.
Okay, 200 bytes starting at 1,000.
And let's say the system's MPS is 128 bytes, and the RCB is set to 64 bytes.
MPS 128, RCB 64. Got it.
Okay, so the data comes back like this. The first return packet, CPLD, starts at 0 by 1000. Since the RCB is 64 bytes, it can only contain 64 bytes, ending is 0 by 103F, which is the first RCB boundary after the start.
Even though MPS was 128.
Correct. RCB limits it here. The second packet starts at the next RCB boundary, 0 by 1040. Again, it can take 64 bytes, ending at the next boundary, 0 by 107F.
Okay, so that's 128 bytes total so far. Needs 72 more.
Right. The third and final packet starts at the next RCB, 0 by 1080. Just needs the remaining 72 bytes to complete the request. So it goes from 0 by 1080 up to 0 by 10C7, which is the end of the 200 bytes you asked for.
And that's less than MPS and doesn't cross an RCB.
Exactly. So that 200-byte request resulted in 3 return packets, 64 bytes, and 72 bytes, all because of the interplay between the requested amount, the MPS limit, and the RCB segmentation rule.
Wow, okay, so RCB is like the defined size of the compartments the data must fit into?
Yeah, the boundaries.
And MPS is the maximum amount of stuff you can put into any one compartment.
That's a great way to put it. And ideally, for the most efficient packing, you'd want your MPS to be a multiple of your RCB, right? If MPS is 128 and RCB is 64, you can potentially fill packets nicely. If MPS was, say, 128 and RCB was something weird like 96, you might end up with more awkward, partially filled packets sometimes.
Makes sense. Okay, we've got a much better handle now on what these parameters are and how they all interact. MPS, MRRS, RCB. Now, let's talk configuration again. How are these actually set in our computers? You mentioned BIOS and registers.
Right. So as we touched on, MPS and MRS are ultimately set via those device capability registers, what the device can do, and the device control registers, what it's told to do in each PCIe device's configuration space.
And the BIOS does the first pass.
Exactly. When your computer first boots up, the BIOS goes through a process called enumeration. It talks to all the PCIe devices, reads their capabilities, including their maximum supported MPS, and then it sets the initial operational MPS, often based on that system-wide weakest link idea, or maybe a default policy. It also usually sets initial MRRS values at the same time.
So the BIOS lays down the initial law. But what happens when Windows or Linux boots up? Does the OS get a say?
Oh, absolutely. The operating system can definitely influence these settings and sometimes even override what the BIOS did. Linux, for example, gives you quite a bit of control through kernel boot parameters.
Ah, those command line options you mentioned.
Yeah. Using cboost tune-off just tells Linux hands-off, use whatever the BIOS set.
Okay.
cboost safe is more conservative. It looks at all the devices connected downstream from a root complex or a bridge and sets the MPS to the largest value that all of them commonly support.
So a safer common denominator.
Right. Then there's cboost. That's the one that tries to be smarter, setting MPS based on the connection right above the device and the device's own capability. And crucially, This mode usually caps the MRRS to be no larger than that locally determined MPS.
The balanced approach we discussed.
Exactly. And finally, there's a CBIS peer-to-peer. This one forces a very low 128-byte MPS across the board.
Why would you ever do that?
It's mainly for ensuring maximum compatibility in complex setups, where devices might need to talk directly to each other, peer-to-peer, without necessarily going through the main CPU root complex path reliably. It prioritizes compatibility over potential speed.
Wow, okay. That's a lot of different strategies. It really sounds like the OS is trying to balance raw performance against making sure everything actually works together reliably.
That's the core challenge. And it's an ongoing process. There have been recent efforts in the Linux kernel, for instance, to be more proactive about maximizing the MPS settings right at the root ports, those direct connections to the CPU during boot up, trying to establish a faster baseline from the get-go.
What about changing things after the system is up and running? You mentioned LSPC and setPC.
Yeah, LSPC is fantastic for just looking at the current MPS and MRS settings for all your devices. It lets you see what the system decided on.
Okay.
setPC is the more powerful tool. If you have the right permissions, usually root or administrator, you can use it to write directly to those PCIe configuration registers. This means you could potentially change MRS on the fly.
Good.
Yeah, you sometimes see hardware vendors, especially for high-performance network cards, providing specific stepchild commands to tweak MRS for better throughput.
But what about MPS? Can you change that dynamically?
Generally, that's much riskier and often not recommended, or even possible.
Why not?
Well, the devices have already negotiated and are operating based on a specific MPS. Changing it unexpectedly can cause confusion, lead to errors, instability crashes. Most operating systems and drivers, like in Windows, just don't support dynamic MPS changes. If you hot plug a device with a lower MPS capability into a bus already running at a higher MPS, it might just not work correctly until you reboot the whole system. MRRS is generally considered a bit more flexible for dynamic tweaks in certain situations, but MPS is usually best left to the BIOS or OS boot time configuration.
So it really reinforces that idea.
Yeah.
The best configuration is highly context dependent. There's no single magic bullet setting.
Absolutely not. It depends entirely on the hardware, the OS policy, and what you need the system to do.
Okay, so we've dug into the what, MPS, MRRS, RCB, and the how configuration. Now, let's really focus on the why this matters for you, the listener. What are the key factors that influence how we should think about MPS and MRS for our own system?
Okay, several crucial things come into play. First and foremost, hardware capabilities.
Right, the weakest link idea?
It's exactly. The supported MPS listed in that device capabilities register for every component in the path CPU controller, motherboard switches, the endpoint device itself, like your GPU or SSD, that sets the absolute upper limit.
Yeah.
You just can't go higher than what the hardware physically supports.
And you said that's often lower than the theoretical 4.96 max.
Often, yes.
Yeah.
In the real world, especially on consumer hardware, seeing MPS operate at 256 bytes or 512 bytes is very common, even if some components technically could support more.
Okay. What about the layout of the system? The topology and hierarchy? Does how complex the motherboard is matter?
It definitely does. In systems with lots of PCIe slots, maybe multiple switches connecting them, that's where that smarter hierarchical MPS configuration like Linux's SUBIS perf really shines.
Right.
It lets faster parts talk fast without being held back by slower segments elsewhere. But if you have a setup where reliable peer-to-peer communication is critical, you might need that more conservative, lower uniform MPS type of peer-to-peer just to guarantee compatibility across all possible paths.
You also mentioned buffer sizing earlier. Can you elaborate on that? How does MPS affect the physical hardware needs?
Sure. A larger MPS setting means a device needs to have enough internal memory, enough buffer space, to actually hold those larger incoming packets while it processes them. So bigger MPS generally implies a need for bigger physical buffers on the device.
Okay.
But there's a subtle point, too. While the size needs to be larger, the fact that you might be dealing with fewer, larger packets overall could potentially influence the depth or number of buffers needed. The longer time it takes to transmit one big packet might help absorb some of that back-and-forth latency, potentially reducing the need for super deep queues in some scenarios.
Yeah.
It's a complex interaction.
Interesting. Now, a big one. What about what I'm actually doing on my computer? How do different application workload characteristics influence MPS and MRRS choices?
This is absolutely key. If your main use involves bulk data transfers, think copying huge video files, working with really fast NVMe storage, high-speed networking like 10GE or faster,
Yeah.
you'll generally see the most significant benefit from larger MPS and MRRS values. Larger packets mean less overhead percentage-wise, boosting your effective throughput.
Makes sense.
Conversely, if your workload is mostly lots of small, latency-sensitive packets, maybe control messages, certain types of online gaming packets, quick database lookups, the MPS setting itself might not change the size of those already small packets much.
Right.
However, having a well-configured MPS for any larger background transfers happening can make the overall bus more efficient, which could indirectly reduce queuing delays and improve responsiveness for those small packets too.
Okay. And read versus write.
If your work is heavily read-intensive, loading massive game levels, pulling large data sets from storage, then MRRS becomes particularly important. A larger MRRS helps stitch that data much more efficiently with fewer request round trips. And if you're doing a lot of writing data, that's where MPS has a more direct impact, determining the size of the packets carrying the data you're sending out.
Lastly, what about just keeping things running? System stability and compatibility. How much should we worry about that when thinking about tuning?
Stability always has to be the priority. Always.
Right.
While it's tempting to think you can just crank MPS and MRRS up to the max supported values and get free speed, you run a real risk of pushing beyond what your specific combination of hardware and software drivers can reliably handle.
And that leads to
Unpredictable errors, maybe silent data corruption, system hangs, blue screens, crashes, you name it.
yikes.
The default settings chosen by your BIOS and OS are usually there for a reason. They aim for stability and broad compatibility across a huge range of hardware combinations. So while tuning can yield benefits, you need to be cautious and understand the potential downsides if you stray too far from defaults or vendor recommendations.
Okay, caution is key. So it's a really intricate balance with all these factors interacting. Let's dig into the measurable performance impact now. How do these settings actually affect things like bandwidth and latency?
Okay, bandwidth utilization is probably the most direct impact. Like we said, larger MPS values reduce the proportion of fixed overhead, the packet headers, error checking codes, stuff like that, compared to the actual useful data payload.
So more data, less tax.
Exactly. For large file transfers, moving from, say, a 128-byte MPS to a 512-byte MPS can make a noticeable difference in the effective speed because a much higher percentage of the bits flying across the wire are your actual data. We did some calculations. The efficiency gain can be quite significant. And similarly, on the read side, a larger MRS reduces the overhead associated with sending all those ASC packets, freeing up more bus time for the actual data to come back.
Okay, bandwidth seems clear. What about latency, the delays we actually perceive?
Latency is, well, it's a bit more nuanced.
How so?
For large data transfers, somewhat counterintuitively, a larger MPS can sometimes reduce the overall time it takes to complete the entire transfer.
Even though each big packet takes longer to send.
Right, because you're sending far fewer packets in total. This means less time spent on the overhead of initiating each packet, less potential waiting time for bus access, fewer acknowledgments needed. So the total end-to-end time for the whole chunk of data can be lower.
Okay.
But for small data packets or control messages, the MPS setting itself doesn't really change the inherent latency of sending that one small packet. Its size is already small.
Right.
However, as we mentioned, if the overall bus is running more efficiently because background large transfers are using a good MPS, it can indirectly reduce queuing delays for those small, latency-sensitive packets. Less congestion overall.
Makes sense. And the MRRS impact on read latency.
That can be quite significant for reads of large data blocks. A larger MRRS dramatically cuts down the number of request round trips needed. Asking for data, waiting for it, asking again. Doing that fewer times directly reduces the total time it takes to start getting all the data back. You might see, maybe a 10% or more improvement in some I/O-heavy workloads just from optimizing MRRS.
So it really sounds like there's often this trade-off to consider. Bigger MPS potentially boosts throughput for large files, but might slightly increase the serialization delay for any single large packet.
Precisely. And that Linux strategy, SHEBA-SPERF, limiting MRRS based on the local MPS, that's often trying to find a good balance between read efficiency, MRRS, and write completion efficiency, MPS. It aims for good overall system responsiveness. not just maxing out one metric at the expense of others.
Gotcha. Now, PCI itself hasn't stood still. We've gone from Gen 1, way back when, up to Gen 5, widely available, and now Gen 6 is rolling out. How have MPS and MRS evolved, or has their importance changed with these faster speeds?
It's quite interesting. The fundamental rules, the way MPS and MRS work, and even their maximum defined values, still up to 4096 bytes, have stayed remarkably consistent all the way from PCIe Gen 1 right through Gen 5.
Really? No major changes?
Not in the core definitions or limits. The PCI SIG, the group that manages the standard, puts a huge emphasis on backward compatibility. So even modern hardware, like Intel's latest F-Tile IP for FPGAs, still supports that same range of MPS settings.
But surely the much higher bandwidth of, say, Gen 4 or Gen 5 compared to Gen 1 must change how important these settings are.
Oh, absolutely. The increased link speeds definitely amplify the need for efficient packetization. Getting MPS right becomes even more critical to avoid wasting that precious extra bandwidth.
How so?
Well, another factor is the encoding efficiency. Later generations, Gen 3 onwards, use a much more efficient 128B, 130B encoding compared to the old 8B, 10B.
Less overhead in the encoding itself.
Right, which means the fixed overhead within the TLP packet itself, the headers and stuff, becomes a relatively larger percentage of the total bits being transmitted at those higher speeds.
So optimizing MPS to make the data payload as large as possible relative to that fixed overhead matters even more now.
Exactly. You need efficient packets to really leverage the raw speed of Gen 4, Gen 5, and beyond.
Okay. And now the really new stuff, PCIe 6.0, with its FLIT mode. That sounds like a bigger shift. How do MPS and MRS fit into this new FLIT world?
PCIe 6.0 does introduce a more fundamental change with its flight flow control unit mode. Instead of sending variable-sized TLPs directly over the wire, it breaks data down into fixed-size 256-byte chunks called FLITs for transmission.
Fixed size. So no more variable MPS on the wire itself.
At the physical transmission layer, yes, it's fixed FLITs. This approach actually helps reduce some of the traditional overhead, like needing CRC checks per TLP. Now it's per FLIT.
Okay. So does MPS even matter anymore in 6.0?
It still does, conceptually. Right. Interestingly, even with FLIT mode, the guidance and design recommendations often still encourage aiming for something like a 512-byte MPS at the logical TLP level before it gets broken into FLITs.
Yeah.
It likely relates to buffer management and how data is processed internally before hitting the wire. Also, one potential benefit of FLIT mode is that it might eventually allow for more flexible, maybe even dynamic changes to the effective MPS setting without disrupting traffic as much as in older gens. And it could make supporting different MPS values in different parts of the system easier.
So maybe more intelligent optimization in the future.
That seems to be the direction. The trade-off between link efficiency, favoring larger logical payloads before FLIT conversion, and latency, where smaller chunks might be slightly faster individually, still exists, though.
And anything else in 6.0 relevant here?
Well, PCIe 6.0 also massively increases the number of tags available. These are used to track outstanding read requests. It goes up to 14 bits.
Wow.
While not directly MPS or MRRS, having more tags means the system can handle many more pending reads concurrently. This could make using larger MRRS values even more practical and beneficial on these ultra-fast links, as the system is better equipped to manage the potentially large number of completions coming back.
So the core concepts of MPS MRS persist, but their optimization and interaction with new features like FLIT mode and more tags will continue to evolve.
Exactly. The focus might shift slightly towards managing lots of concurrent, maybe moderately sized transactions very efficiently, rather than just pushing for the absolute largest possible single packets in all cases.
It's fascinating how these low-level details have to adapt. Okay, let's bring this right down to earth. What MPS and MRS values do we actually see in the computers people are using today? And maybe some specific tuning tips for common hardware like NVMe drives or GPUs?
Great practical questions. While the specs allow up to 4096 bytes, what you typically find in real-world systems is often a compromise.
What's common?
In many current consumer systems, seeing MPS set to 256 bytes or 512 bytes is very frequent, maybe 512B becoming a bit more common as a default on newer platforms. MRS also often defaults around 512 bytes, although, as we said, many devices can support and be configured for much larger values. Older systems, you'll definitely see smaller values, like 128 bytes being common.
Okay, so what about specific hardware? Let's say someone has a fast NVMe SSD. Any thoughts on tuning there?
For NVMe drives, yeah, there can be benefits, since NVMe often deals with data internally in 4 kilobyte blocks.
Right, 4K alignment is a big thing.
Exactly. It may be beneficial to set the MRRS to a value that aligns well with that, maybe 2048 bytes or even 4096 bytes if your system supports it. The default is often just 512B, and sometimes bumping MRRS up can help saturate the PCIe link better, especially for sequential reads.
Do NVMe drives have their own MPS MRS settings?
Yes, the NVMe specification actually includes fields for the drive to report its MPS capabilities and for the host to configure both MPS and MRS for that specific drive. However, be aware that some drives, especially older or maybe lower-end ones, might have a fixed or limited maximum MPS, sometimes even just 128 bytes, which could be a bottleneck.
Good to know. What about graphics cards, especially for gaming or maybe HPC?
For high-end GPUs, getting data in and out fast is critical. Recommendations can vary a lot by vendor NVIDIA, AMD, Intel, and even specific card models.
What are any general trends?
Sometimes you'll see recommendations, particularly in HPC contexts or from network adapter vendors working with GPUs, like Mellanox NVIDIA, to set the MRS to the maximum supported value, often 4096B, if the whole path supports it.
Why?
To help the GPU fetch textures, model data, or whatever it needs from system RAM as efficiently as possible with minimal request overhead. It's also worth noting other related PCIe settings might matter for GPUs, like enabling extended tags to handle more outstanding requests, or sometimes even disabling features like Access Control Services, ACS, for things like GPU direct peer-to-peer transfers, though that has security implications. And just to be clear, sometimes NVIDIA talks about MPS for their multi-process service feature that's different from PCI MPS.
Ah, good clarification. Okay, one more. High-speed network cards, like those used in data centers or for RDMA.
Right. For things like Roscien is doing RDMA, performance is paramount. Here again, larger MRRS values, often pushed to the maximum 4096B if supported, can yield significant throughput gains.
Why there specifically?
Because RDMA often involves transferring large blocks of data directly between systems with minimal CPU involvement. Reducing the read request overhead with a large MRRS is key to achieving line rate on fast networks. Many high-end NIC vendors provide tools to query and set MRS, but again, workload matters. Optimizing for tiny packet latency might involve different settings like queue sizes, interrupt moderation, than optimizing for bulk transfer throughput where MPS and MRS are king. Enabling relaxed ordering can also help performance sometimes.
So it really sounds like for peak performance on specific hardware, looking at vendor recommendations and maybe doing some careful testing is often the way to go, rather than just assuming defaults are optimal or maxing everything up blindly.
Exactly. Achieving that last bit of performance often requires a holistic view. It's not just MPS and MRS. It's also about DMA alignment, UDMA locality, which CPU core and memory bank are closest to the device, interrupt handling, queue depths. All these things interact. And sometimes you might find your hardware can actually support higher values than initially advertised or configured. But empirical testing is really the only way to discover that and verify stability for your specific setup and workload.
This has been incredibly illuminating, a real deep dive into the guts of PCIe performance. To wrap this all up, what are the absolute key takeaways you want listeners to remember about MPS and MRRS?
I think the main things are MPS and MRS are fundamental PCIe settings. They really matter for performance, influencing both bandwidth and latency.
Right.
MPS controls the size of the data payload in packets, impacting overall efficiency for both reads and writes. MRS controls the size of read requests, mainly affecting how efficiently you can ask for large amounts of data.
And configuration is key.
Yes. Configuration depends on hardware capabilities, that weakest link, system software policies set by the BIOS and OS, and crucially, the demands of your specific workload. And remember, there's no single best setting that works for everyone. It's about understanding your system.
And it sounds like even with PCIe 6.0 and FLIT mode changing the physical transmission, these underlying concepts, efficient packetization, efficient requesting, they're going to remain critical for getting the most out of future high-speed interconnects.
Absolutely. As speeds keep climbing, managing data movement efficiently at this low level becomes even more important, not less.
So here's a final thought for you listening. Maybe take a moment sometime, see if you can use tools like LSpaceI on Linux or similar tools on other OCs if available, to just look at the MPS and MRRS settings for key components in your own computer, your graphics card, your NVM drive.
Yeah, just be curious.
Think about how your typical usage, gaming, video editing, editing, coding, whatever, might relate to the concepts we've talked about. You could even look up the specs for your motherboard or GPU online and see what MPS values they officially support. It might give you a whole new appreciation for the hidden complexity humming away inside your machine.
And hey, if you do explore your system's configuration, or maybe even carefully experiment with some settings based on vendor advice, always back up first. We'd genuinely be interested to hear about it. Share any insights you gain or any further questions that pop up about PCIe performance tuning. It's a deep topic.